We're speeding into the fast lane with Globe's 5G technology. It's fast, it's fun, it's wonderful. It's Kim Son-ho approved. With Globe 5G technology, the possibilities are endless. It's about time we inspire the youth to create something meaningful, spark reinventions, and improve the framework of the future. That's what the 5G hackathon is about. Students, professionals, and startups are welcome to join the event by registering using this link. Once accepted, you may enjoy access to the Globe 5G Hackathon HQ, where the enablement workshops will happen. That's 2 weeks worth of fun workshops and mentorship by industry experts from our tech partners. All these to get you to the top. That doesn't end there. Apply what you've learned from the workshops and pitch your idea on how you can use 5G to improve the way we live. The panel will pick the top 30 semi-finalists to join the pitch competition and enjoy exclusive workshops and consultations with mentors. But if you're truly, madly, deeply at the top of your game, you can be chosen as part of the top 10 finalists who will proceed to the hackathon finals. 3 of the best pitches will be hailed as winners. What's in it for you? Well, over 500,000 pesos worth of prizes will be given away, plus a chance to be part of the Venture Builders program of 917's Venture Velocity and work directly with Globe 5G Acceleration Lab. This is powered by Globe and Animal Labs by DLSU. Thanks to 5G, we're about to achieve great heights. Click the link and show us what you've got. Get ready to reinvent your power to create change. Register now.
Do you want to make a difference and reinvent your world? 네, 안녕하세요. 여러분, 김선호입니다. 샌드박스 같은 곳에서 경쟁하는 기분을 느껴보고 싶으신가요? 그렇다면 글로브 5G 해카톤에서 진행하는 워크숍과 멘토십을 통해 5G 활용 방법을 만들어보고 여러분의 친구, 동료들과 팀을 만들어서 디지털 시대 속 필리핀의 새롭고 흥미로운 가능성을 열어보세요. Follow your dream. Register now.
Watch me do my thing.
Take it to the next level with Globe's fiber, LTE advanced, and 5G mobile connection. Now you have the power to reinvent your world. Globe.
The new mind-blowing Surfer All 99?
9 gig? All sites?
For all devices?
Shareable with up to 4 people?
Like my family? Anywhere they are?
new mind-blowing Surferall 99.
Dear Mother, light of the home.
Dad.
Hey, baby!
Greetings, Professor Rodolfo.
May I be absolved
From
Math club tomorrow.
May Globe Virtual Hangouts kasi.
Go and hang out from wherever you are. Just open the Globe One app, choose an event, and click join.
Watch concerts online!
dance together.
We can do quiz nights.
Yo, let's go! If you allow me,
I promise.
To make it up to you.
And repay your kindness tenfold? Truly, your favorite child.
I love you, Dad.
please, babe.
Thank you, sir.
Enjoy your fave events with Globe Prepaid Virtual Hangouts. All together now.
Yes!
Get it? Get it? Yeah.
Hello everyone. Welcome to this session on enabling cloud to edge digital transformation from AWS. My name is Owen Law. I'm a senior partner solutions architect focusing on the telecom segment across APJ region. My main remit is to support telecommunications ecosystem partners and telco customers and help them adopt cloud technologies. It's our great pleasure today to spend this time with you a little bit about the 5G edge computing use case we've supported and we observed from the market, as well as some of the solution enablers we have introduced into this space. And hopefully those are useful addition to your ideation for the 5G hackathon. Before we start the actual session, let's talk about what we will cover today. So we will cover a number of topics. We will start with a bit of sharing about, what are these use cases that we are talking about, who has done them before, what are the key learnings. We will also zoom into, what is edge computing and why is it important, and what are the architecture implications of edge computing. And then we will specifically dive a little bit into 5G. Especially we want to focus on, well, when 5G and cloud technologies come together, what are the new innovation and possibilities we can enable? Then in section 4, we will have a fairly comprehensive overview of some of the key AWS enabling services for the edge. And we want to give you that overview so that you can think about how you might leverage these enabling services in your hackathon use case ideation. And of course, we also want to share with you a little bit about market realities. Basically, when you think about your hackathon ideas, You also want to think about, commercialization, pathway to adoption, and hopefully us sharing those market realities will help you kind of qualify, identify the right use case. And then we also want to give you a bit of a hands-on demo just to show you a simple example of how you can run a 5G network on AWS. Finally, we will do a bit of a Q&A session and wrap up, and share with you some of the learning resource which you can leverage after the session. And to facilitate, capturing your questions during the session as you go through the session, we set up this upvote link. So feel free to pop your questions in as you go through them, go through the session. You can ask a new question or you can upvote someone else's question. We're going to spend some time during the Q&A part to go through, whatever questions were captured here. So let's jump right into it and look at what are the innovative use case that's been done so far. I thought it might be a very interesting exercise just to start with a bit of a brain teaser. So here we're showing you 4 use cases. Each one of them have leveraged 5G and edge computing in a unique way. I want you to spend the next seconds just to think about how 5G or edge computing have been applied in each one of these use cases. So spend the next 5 seconds just fashion a guess. We will review the answer after 5 seconds. All right, so hopefully you had a chance to think about it. In fact, these 4 use cases are, very different use cases. On the top left corner, we have a connected 5G airport use case. The objective of this use case is to basically enable a seamless traveler experience. If you recall from the pre-COVID times, as a traveler, as you navigate through the airport, chances are you end up with a lot of queues that are for luggage drop-off or for security checks. And you also have trouble navigating your way through the airport, finding restaurants or finding the boarding gate. And you can imagine in the post-COVID time, of things like safe distancing and all those additional measures, this experience is likely going to get even more troublesome. So what this use case have achieved is by furnishing the airport environment with 5G, we can then deploy the security, smart cameras a lot easier in a lot more distributed fashion across the airport area, and use those smart cameras to automate, luggage drop-off, to automate security checkpoints, so that you reduce the queuing time your travelers spend in the airport. At the same time, we can also use the connected 5G foundation to enable augmented reality assisted mobile application, so that you get very prescriptive, personalized, contextually aware guidance to point to where you want to go around the airport. And you can also receive notification about when boarding is happening and direct you to the gate. So that's the first use case. The second use case is something fairly different, where this is a remote robotics, basically automation use case. So it's a fairly interesting use case where we combine 5G edge compute capabilities with robotics. And this is to support some very specific implementation, like deploying this robot in extreme environment conditions or military use. So we actually have a video to show you more about this use case on the next slide. The third use case, if you look at the bottom right corner, is a connected stadium use case. In this particular scenario, the stadium is furnished with 5G. And using that foundation, we can actually enable use cases such as crowd analytics, or you can use that to deliver immersive sports viewing experience on a mobile app by combining augmented reality with what the viewers can actually see inside the stadium in real time. And then the final use case is what we consider a city-wide use case, where in this particular scenario, the first responder, like police or the fire department, these first responders are carrying body-worn camera, and as they go to perform the different missions across different metro areas, they can actually get real-time augmented, object or video detection capabilities, which will help them understand their surrounding, get real-time alerts on specific events, and all this is enabled by edge inference capability that are deployed on 5G mobile edge cloud. So as I suggested before, we want to show you a very quick video about the robotics use case. So what you're seeing is something we did in partnership with a company called Robotics. Here, what you see is this is a highly intelligent, highly mobile robot, which is actually came equipped with an AWS edge compute, as you show in this black box attached to the robot. These robots are built for missions, and they have capabilities that can go into many different location environment. It can be inside a factory, go underground, go into a mine, and go to some very harsh conditions in general. And because of that nature, in many cases, the robot does not have good wireless radio coverage. So in order to overcome that challenge, we work with Ghost Robotics and a number of network vendors to basically equip things like wireless modem and also antennas, plus a very lightweight mobile packet core, so that these components can be deployed on the robot itself. And with that capability, the robot can actually form mesh network with each other, or they can form mobile network access point so that they can interact with surrounding sensor or endpoint device. And this actually enables them to operate in a disconnected fashion. So I also want to show you a quick video of the second use case around cloud analytics.
Hello, my name is Ray Gibson, and I am Vice President of Engineering at CrowdVision Inc. My team and I work with various sensors to do crowd analytics in large spaces. When we combine multiple angles and sensors together, we can generate a very detailed 3D point cloud of the space. It's a very high bandwidth operation, which makes Verizon 5G an excellent choice for pushing that bandwidth up. The accuracy of the sensors that we use allows us to provide several useful analytics. This range from occupancy, how many people are in a space, flows, how many people went through a certain doorway, wait times for lines, and also social distancing, where we can measure the exact space between people and get an understanding of how well the crowds are applying social distancing. With this information, we can then help the customer load balance. Maybe the restroom line here is really long, but if you go upstairs, you won't have a wait. Maybe you can go to a different concession stand. Maybe you can go through a different security checkpoint line. One of the biggest challenges to getting our product installed is the vast infrastructure requirement. Typically, we require miles of Ethernet cable, racks full of servers and things. Being able to use Verizon 5G and AWS Wavelength to do that processing and that backbone significantly opens up the opportunities of the places and the locations that you might be able to place equipment. So far, we've seen some really great results using the 5G technology combined with AWS Wavelength. We see a bright future where we are deploying at venues around the country and using our data to help the venues reopen safely.
So what's interesting about this use case is how by using 5G, we actually help overcome one of the pain points described, which is the cabling, the physical wiring to implement these sensors. And because using wireless technology, you can actually get rid of those wires and making that infrastructure deployment a lot easier. And the second area where this is very beneficial is you can imagine it will get very expensive to implement these compute and storage platform in every single venue. So by moving those capabilities into a mobile edge cloud, we can actually support multiple of these venues from a single sort of mobile edge location. And beyond those two use cases, I also want to share with you some of the partnership success we had with telcos across the globe. If you have been following us closely, what you have noticed is we have been quite successful in launching 5G mobile edge cloud alongside Verizon in the US. Today, we already have up to, I think 10 different locations across US where we have the AWS Wavelength offering. In Europe, we have been working with Vodafone very closely to drive their ecosystem incubation. So we help them run this Edge Innovation Program, which is kind of an open invitation to startups and developers that have great innovative ideas around 5G and edge computing. And they can submit those ideas, and through a selection process, the winning use case will actually get go-to-market support to help them turn those ideas into reality. In Japan and Korea, we have been closely supporting the operators there to create service bundle for B2B and B2C and B2B to X customer. So these are in the form of immersive AR experience for entertainment, or it could be collaboration with museums or shopping district to again enable immersive shopping experience. The last but not least is our collaboration with Dish Network in US. This is a very, very recent announcement. And this partnership actually talks about how we help them deliver 5G network on the AWS platform. And of course, towards the end of last year, we also announced our collaboration in Telefonica with Ericsson to enable 5G private network solutions that are specifically catered for Industry 4.0 use cases. So another perspective we want to share from a use case perspective is many of these use cases often happen in a broader context of digital transformation. So here we pick 3 example industry, and we observe there's some similarities or kind of common pattern across them. AWS is very fortunate. We literally have sort of the front row seat in many of these digital transformation initiatives because we support many industry vertical in their digital transformation journey. And what we notice is a lot of these transformation actually start from the physical edge. So when you look at, let's say in manufacturing, a lot of what they're trying to do is turn their decade-old factory plant, the machinery from analog into digital solutions, and then implementing sensor technologies and actually automate that process in a in a factory or in an industry plant. If you look at healthcare, a lot of the effort is spent modernizing. Hey, we have been relying on face-to-face interaction with our patient. How do we transform that into a new form of interaction? How do we deal with very high amount of high fidelity medical imagery? So for the second topic, we want to zoom into the notion of an edge architecture. What is the edge? And why is the edge important? What are the architecture implications? First question is, well, what is the edge? The reality is there is no specific definition of the edge. It could be anywhere. It could be your mobile terminal. It could be a connected vehicle. It could be in a factory floor. It could be in a container ship. It really depends on where the end users are. And also it's a factor of balancing a number of considerations, as you will see later on, about cost and implementation complexities, physical distance, all those factors. The edge is where we can optimally offer compute and processing capability as close to the user as possible. And then the second question is, well, why does edge actually matters? Why is it important? Well, here we try to plot out some of the common applications that we came across, and we plot them against the bandwidth needed to enable this application, as well as their latency requirement. And what we see is, you take an example of a 360 video where you likely have to combine multiple video streams from different angles. And by its nature, it's something that requires very, very high bandwidth. But since this is a video distribution use case, you are probably okay, you can tolerate, latency in the order of seconds. Whereas you look at something like robotic system control, these are very frequent but very small transaction, but it has a very, very stringent latency requirement. In many cases, it can get to milliseconds or less than that. And then for telcos, one very prominent use case we're seeing as an emerging use case is the space of Open RAN and Virtual RAN. In that particular scenario, because it's supporting a mobile network, we're talking about fairly high level of bandwidth. At the same time, because of the nature of radio control, it actually has a very low tolerance to latency. So it needs to be delivered in milliseconds. So when we look at all these different use cases, they actually have different performance profiles. And this is a very important consideration when it comes to how do we enable these use cases. Can we enable them using one type of edge solution, or we actually need a variety of edge solutions to enable these? The other very important consideration is edge computing is actually very hard to do when it comes to real-world implementation. There are certain things that we have to balance and kind of think about together. One is the law of physics. We can't overcome speed of light, so to speak. So whenever we implement certain things that are a particular distance away from the end user, there's always going to be latency involved. And then the second consideration is law of economics. The more you distribute, the more endpoints you need to manage, and likely the higher cost it is to deliver and operationalize on an ongoing basis. Whereas if you can centralize these implementation, you get economies of scale, you have lesser endpoint to manage, and chances are it will be cheaper to do so. And then the third dimension is what we call the law of the land. So that means there are things like regulatory requirements, data sovereignty requirements, geographical constraint, where sometimes you have to localize the compute storage capability because of law of the land. So from an AWS perspective, our vision is we want to give you centralized control and decentralized execution when it comes to the edge. And what we mean by that is we want to bring those computing storage capability and reduce latency as much as possible. But at the same time, we also want to make sure we offer a very rich set of cloud services so that you can use them everywhere. And then depending on the edge scenario, we also want to offer edge-specific capabilities. And you will see some examples of that in later session. And then the last part is very important, is we understand there will be many different permutations of the edge. We understand there are different edge deployment scenarios, but we want to make sure that all these are done, whether it's in the edge or the cloud, they can be controlled and enabled by a single programming model. One more point on this is the concept of location is actually very important in any 5G edge discussion. So here you take two example use cases. On the left, you have a mobile cloud gaming use case. On the right, you have a AR-assisted industry asset inspection use case. Well, what's interesting is when you look at these two use cases, we're talking about two very different types of locations. The one on the left, the cloud gaming use case, is where consumer, they want to be able to pull out their mobile phone and enjoy that immersive gaming experience everywhere they go. So the requirement for this edge capability is kind of like everywhere in a metro city. On the use case on the right is where, this is an experience you're expected to deliver in very specific location, specific factory floor, for a very specific industry vertical. Which leads us to the notion of the edge to cloud architecture. From an AWS perspective, we have worked with many customers to understand their needs. And we essentially see that for us to be successful, we need to consider a continuum of capabilities that can meet different types of edge application needs. What you will see is we obviously have our foundational capabilities in the cloud region. These are fairly centralized locations. We have quite a few of them across the globe. At the same time, we also understand the importance of making cloud capabilities available in largely populated metropolitan areas. We need to make it available on-premise. We still see a lot of enterprise have requirement of on-premise compute, whether it's in their own factory floor or in a co-location data center, or even in partners data center. And then there are scenarios where we need to deploy these capabilities in unconventional location. So we're not talking about data center. It could be out in the field, on remote vehicles. It could be in ruggedized environment. And then one thing we've seen is the emergence of 5G being an important connectivity technology. So we want to make sure that cloud capabilities can be offered in a very low latency way to 5G connected device. And then towards the left-hand side of this diagram, we are more focused on private network scenarios, or all the way into microcontrollers, IoT device, which are sitting on kind of the far edge type locations. So what this means is, if you look at the AWS sort of cloud to edge architecture and service capabilities, today we have the cloud regions. I also talk about how we're addressing the need for metro city centers, cloud platform needs. And this is something enabled by a service called AWS Local Zone, which is infrastructure we deploy into these metro locations. For 5G networks, we have an offering called AWS Wavelength, which is a very specific motion we have with telco partners. So we work with them to implement AWS Cloud right next to their 5G network. For on-premise use case, we have a solution called AWS Outpost, which is a fully managed infrastructure offering where we can implement in any customers, any enterprise on-premise location. And this is supplemented by another set of solution, the AWS Snow family, where we can actually take Snow family device, which are very compact, small form factor, portable device. Some of them can even work in ruggedized, disconnected environment. So we can drop this device into some of those remote and distributed unconventional location. And then if you look at the left-hand side of this diagram, we also have capabilities very specific to IoT and microcontrollers. So this is a whole new set of services on its own, and we'll talk a little bit more about that in subsequent section. The last one I want to point out is our container platform. So this is definitely an area that is growing in importance. So we have specifically made available our managed Kubernetes services so that it can operate in the cloud and also in hybrid on-premise environment outside of AWS, as well as an EKS distribution, which is a container distribution that you can actually take and deploy in any location of your choice. So the final sort of part we want to share is, when you think of the need for different types of edge platform, one thing we also want to point out is edge infrastructure platform is just one piece of the whole puzzle. When you look at any 5G edge computing use case, you can see that many of them is enabled by a combination of horizontal enablers. So these are capabilities, technologies that you repeatedly see across different types of 5G edge use case. And the example of this is, the mobile network itself is something that you will see in many of these use cases, as well as the edge infrastructure, the actual compute storage platform that you deploy on the edge. Again, you can see those type of platforms in many use cases. There are other examples like IoT capabilities, video surveillance capabilities, AR, VR backend. All those are things that you might see recurring, repeatedly showing up in these use cases. And then for different use case, there are also things what we call vertical enablers. So for example, when you look at the cloud gaming use case, there's a very specific gaming front end, back end that is specific to cloud gaming itself. When you look at a solution supporting real-time sports viewing experience, this is again, there's something very specific about implementing sensors, attaching them into the players or around the stadium, and using technologies that specifically to a particular sport. So most of these use cases is a combination of these vertical and horizontal enablers, and we encourage you to when you think of any use case, think about what enabling capabilities do you need, and think about sort of what are the things that you can repeat across use case, or what are the things that are specific to a particular use case. Obviously, AWS and many of our partners are trying very hard to bring these capabilities and enablers together. So for the next section, we want to spend a bit of time looking at 5G on AWS. So I'm sure you have heard a lot about 5G, what its capabilities are. There's more than plenty of industry material out there to talk about it. So our focus is not to repeat those. What we do want to do is recap some of the key characteristics of 5G in the context of what we're talking about, which is 5G and edge computing. So if you look at this pyramid, if we start from the top, one very well-known, well-defined outcome from 5G is the speed and throughput improvement. So we're certainly expecting with 5G technology, the peak data rate mobile users and device will enjoy will be much higher than what it is in the current 4G technology. At the same time, we also expect the average data rate user can experience will also see significant improvement. But what we do want to call out is this is not going to happen overnight, right? This is going to be a combination of how quickly telco operators can roll out the network, the spectrum strategy they adopt, the implementation such as millimeter wave. So it's going to take a few factors coming together in order to get to these type of speed. So in reality, in the first couple of years of 5G deployment, we don't expect these type of speed available everywhere. So and that's a very important point to consider, especially when you think of what are the use case possibilities right now versus medium and longer term. The second factor is often overlooked, which is around connection density. So this is in relation to how many devices we can connect on a per kilometer square basis. So we certainly expect a proliferation of mobile connected device in the next decade. So the ability to connect more device is actually very important. So that's also one of the key benefits from 5G. And then the third part of this pyramid is latency and reliability. So 5G, architecture and standards have baked in, a lot of enablers to help us reduce latency, both user plane and control plane. So again, this is going to bring about actual user benefit, but same with speed and throughput. This is going to take time, right? It's going to take implementation, deployment maturity. So again, we don't expect user will see a huge improvement right off the board, but this will come over a period of time. And on top of that, we also see that 5G can bring about new types of service deployment options and models. We'll talk a little bit about that later. And obviously energy efficiency, this is very critical because a lot of the end user device, they have very small form factor. So anything we can do to improve energy efficiency will be, you'll see a lot of commercial benefits from an end user perspective. And you look at the text on the right-hand side, these are also, describing a lot of the ongoing efforts in terms of standardization, industry collaboration to specifically focus on use cases like public safety, V2X, industrial IoT, ultra reliable low latency, and so on. So these are some of the new use cases we expect 5G will address, over a period of time. And what we do want to talk about is zoom into, the architecture evolution to 5G and how it actually relates to the topic we're talking about today, which is cloud and edge computing. So these are very, very high level depiction of that architecture. There's a lot more nuance to what we are showing here. So so treat this as more of an illustrative architecture for the purpose of our discussion. So if you look at 4G, which is the current mobile technology serving majority of the market today, in the 4G architecture, you have radio base stations that are deployed in fairly distributed fashion. But what you do have is, in most cases, a very centralized core network. So this box, this square here, 4G Evo Packet Core, this is the core network that controls all the mobile base station and interacts with all the connected mobile device out there. And today, these are deployed in fairly centralized fashion. So even if you go to a large country, for example, Australia, chances are you will, you only have a few of these centralized core locations. And then at the same time, today, obviously, we have a lot of applications that are internet-based. So what you will see is potentially from these core network locations, you interconnect with the internet. And of course, we also have a lot of applications that are running in the cloud. So again, the applications could be also sitting in the cloud as well. So this is a very simple depiction of 4G architecture as is. And then as we start to implement 5G, you will likely come across terminology such as non-standalone or standalone network. It is not our intent to cover those terminologies in detail here, but what we want to call out is when it comes to non-standalone network for 5G, what it really means is it is more of a transitional strategy, which allows to continuing using existing 4G asset, especially in the core network, but roll out radio access technology that aligns to 5G standard. So this diagram is showing this part, which is the 4G radio base station, and then the top one is the 5G radio base station that will be rolled out by operators progressively. So in the first iteration, which is the non-standalone implementation, the operator doesn't necessarily need to change much at the core network. So what we're showing is they can still reuse the existing 4G Evo packet core to support 5G. From a signaling and data plane traffic flow perspective, what it means is the mobile terminal will use 4G. You will continue to use 4G for control plane signaling, whereas the data plane portion will go via the 5G radio network. And then from an application perspective, what you start to see is also the notion of mobile edge computing. So this is our ability to implement, cloud storage and cloud processing close to the mobile network. So it's likely you might see, very early implementation of, mobile edge compute, but they will be likely, quite centralized too. So from an application architecture perspective, what you can see in these purple boxes, you can start to see how application can be moved closer to the mobile network. So the real, impact or the real innovation actually starts when we see, 5G standalone network. There's a lot of aspects around 5G standalone network. So we won't have time to talk through all those. But fundamentally, what this is it will require a new 5G, 5G native core. So this core network will support sort of the full suite of 5G capabilities as defined by the standards. At the same time, it will also open up new ways for breaking out traffic and for us to insert mobile edge compute. So here, what you see is instead of bringing everything back to these, couple of centralized locations, we now have the ability to break out traffic using a function called UPF, which is a data plane function. And by breaking out traffic, we can now insert mobile edge computing much closer to the end user as shown on this diagram. So what it means is now instead of having application running in the internet or in a central cloud region, we can now take some part of this application and run it all the way on the edge. And then just also, while we are on this topic of architecture evolution, it's interesting to also call out that, on the radio access network side, there's also a lot of innovation. So you would have heard about, innovations such as, open RAN or cloud RAN or virtualized RAN technology. In a very, very simplistic, sort of term, these are basically taking the monolithic, appliance-driven radio access network implementation of the past and start to disaggregate them into smaller modular software components. And what I'm showing you is example of how those software component will look like. So instead of having one black box sitting in the radio cell site, now you start to see software, your virtualized software modules, and you can be more flexible in how you deploy these software modules. You can potentially deploy them on general purpose off-the-shelf compute and storage platform, and you can start to distribute them. You can have some components sitting all the way at the base station, and some components sitting a little bit further back in the edge locations. So building on that previous slide on architecture evolution, we also want to zoom a little bit deeper into the software architecture of 5G. So here, what I'm showing you is a very high-level depiction of 5G software components. And then I'm also showing you next to it these orange boxes, which shows the 4G software component. So as you can see, there's a few areas where there's overlap. And this is intentional because 5G architecture is essentially derived based on learnings from 4G. So there's a couple areas where they have enhanced, and also there are certain areas where they simply just reuse and leverage. And of course, what you also notice are the new components specific to 5G that wasn't there in 4G before. And what you will notice, for example, is some of the software like this one here, the control plane function. This used to be delivered via 3 different pieces of software in 4G, and they now converge into like a single piece of software. Same case for the user data plane function, where there used to be two separate data plane software modules. Now it's collapsed into one. What's more importantly is the design and architecture principle of 5G. So if you look at the first one, which is control plane and user plane separation, why is that important? Well, it's because we actually want the flexibility to deploy user plane function, which actually handles mobile data packet processing. We want to deploy that much closer to the end user compared to control plane, which potentially can be fairly centralized. So this is, having this will ensure we can, have a lot more flexibility in terms of how we deploy 5G software. Stateless architecture is another great example. In principle, what it does is it basically separates the function that keeps and stores subscriber context, so that you can kind of offload it to a centralized cluster of database, and separate that from the actual function that does the front end processing. So you can imagine when you're trying to deploy a high availability architecture, having this stateless architecture actually makes it a lot easier. So you can make sure you have persistency in the centralized database for subscriber context, but the front end instance can be spin up and down as needed, and they wouldn't impact the continuation of the subscriber session. And then you have service-based architecture, and this is a big deal because in 4G, a lot of these software modules are you can consider them almost like a black box implementation, which are stitched together by standard defined 3GPP interface. In 5G, this has moved to align much better with sort of a cloud native implementation where the interaction between these components are via standard API interface, and then they can be discovered using service discovery mechanism, which are very well practiced already in cloud implementation. So it's a much more modern implementation that way. And then network slicing, I'm sure you will continue to hear a lot about it. But fundamentally, the impact is with network slicing, you can partition up the 5G network in a logical manner so that you can dedicate some slice for highly latency sensitive enterprise application, some slice for general purpose IoT, some slice for a particular enterprise customer maybe. And this gives you flexibility to serve multiple customers, multiple applications, all using sort of the same baseline infrastructure. So those architecture evolution and the 5G architecture principles are very important because we think there's a great opportunity for us to bring the cloud programming model into 5G implementation. And what we have outlined here are sort of 5 key areas of benefits that we think are possible. So if we start from the top, from a scalability perspective, in 4G, a lot of the implementations are done using on-prem, on private cloud, or using appliances. And often you have to predetermine the required capacity upfront, and you wouldn't be able to change the CPU or hardware very often. It's often a 3 to 5 years refresh cycle. On AWS, there is now a great opportunity to leverage a lot of the native scaling capabilities, such as auto scaling group, so you can dynamically scale up and down without having to pre-reserve capacity. Given the 5G architecture we depicted earlier, it is also now possible to take the different 5G modules, they each have their different characteristics, and map it to different types of AWS compute instance. So for example, we have instances that are optimized for compute, instances optimized for memory, instances even with GPU capabilities. So we can take different modules and map it to the right instance and right size those. And then obviously we continue to roll out new types of compute capabilities with more processing power, so on and so on. And that actually, again, it offers a much more future-proof implementation compared to you having to do your 3 to 5 yearly hardware refresh. The second area is high availability. So the stateless architecture that I talked about on the previous slide, it's very important because now you can basically separate the front end processing from the back end subscriber context. And then you can deploy these modules across multiple availability zones to improve resilience. And you can offload those subscriber contexts to managed database cluster, which also has built-in high availability. The third area is around innovation. So because of the cloud native nature of 5G, because of the service-based architecture, now you can actually apply cloud native DevOps and CI/CD approach and use those to drive the deployment, the upgrade, the delivery of 5G software. And what it means is you can potentially make software drops a lot more frequent compared to in the past, in the 4G days where it would take us 6 months to do testing and then 3 months through a rolling implementation window to actually roll out a piece of software. So you end up making like one change to your 4G software in the past, right? And then the fourth area is automation. So we think automation is very critical, given that the complexity of the network continues to increase and the scale of the network also continues to increase. So automation is almost a must. In this case, given the service-based architecture of 5G, which are very API-driven, if you combine that with AWS native service, which are all API-driven, what you can do is have an end-to-end orchestration layer, integrate and interact with the underlying cloud and software components using API, and as a result, you can have a highly automated 5G network. From an infrastructure perspective, we also offer a variety of capabilities in terms of container management, container orchestration, such as our Managed Kubernetes Service, EKS. So most of the 5G software you will see is actually going to be deployed on containers. So as you will see later in the demo, we'll show you what that containerized 5G network actually looks like when it comes to deploying on AWS. The last part is network slicing. So as we said before, this actually gives us an opportunity to partition the network in a logical fashion and assign different resources and components to different slices. So obviously, AWS being very API driven, you can absolutely do that. And in addition, as you will see later on, we also have different types of services. Some of those are smaller form factor service, which you can implement in a private network slice for enterprise. So to sort of contextualize what we just talked about, here's a depiction of a 5G architecture on AWS. As you see, on the left-hand side, we have the AWS region. And what we see is the AWS region is an ideal location for hosting a lot of the 5G control plane and management plane function, as shown in this example here. At the same time, what we also see is the need to support distributed database data plane functions such as UPF, and in future maybe part of the virtualized radio access network, such as the virtual CU example we've shown here. So these are going to be deployed in a distributed fashion, potentially in telcos, edge data center, and we have platforms, as we outlined earlier, such as AWS Outpost, which is a fully managed infrastructure offering we have, which can be deployed on-prem. So potentially these components can be deployed on AWS Outpost. And between the edge and the region, they can be interconnect using reliable, highly resilient, dedicated connections. Using AWS Direct Connect. And in addition to that, we also see these services. These are native AWS management and operations services. These can be services that you can reuse and share across all software components. So today, when you deploy 4G software or deploy your network software on-prem, chances are you will end up with a different suite or different stack of management, logging, and operation tools specific to different vendor solution. Well, if in the cloud scenario, you can now actually have a centralized set of shared services that you can use across the board. And of course, one thing which we don't have time to talk about in this session is to run your 5G network, you also need to integrate that with your operational support system and your business support system, the telco BSS OSS. These can also run in the AWS central region. So in addition to the 5G architecture we shared earlier, which are more geared towards supporting millions of subscribers, many of them could be consumers, we are also seeing the growing importance of dedicated or private network, especially from large and medium enterprise. And what these enterprise demand is, well, can we have the mobile network inside our own premise? Because we have our own set of industrial application, mission critical applications that we want to run on mobile network without wires, basically. And these enterprise location could be an airport, it could be a factory, it could be a university campus, or it could be in a large corporate building. So what we are showing is an illustration of that. If you look at this top part of the diagram, it's showing inside a particular on-premise location, could be a factory. You will have devices such as IoT sensors, cameras. You could have security device. You can have also general user terminals, and they're all connected through wireless network. So the reason why enterprise is looking for this is they see the benefit from a mobile network in terms of coverage, mobility, and performance. And they also want to support mission critical applications on the mobile network. So in the past, a lot of enterprises are hesitant to put really mission critical business application on Wi-Fi. They have to fall back to wired connection for that. But with mobile network, especially with 5G, they see the opportunity now is to go completely get rid of all the wires. And they also see the benefit of having a wireless control plane with quality of service control and so on. And obviously the other factor is security. So in a mobile network, you can use SIM-based security. And the important thing here is we're not saying this will necessarily replace all the Wi-Fi or other wireless technologies on-prem. In fact, it could very well be a very complementary approach such that it can coexist with any existing Wi-Fi technologies. So there are many flavors of private networks, so we won't have time to go deep into every one of those. I'm showing you two very high-level illustrative example here. The first one being you can run a radio network on-prem. You can have a localized data plane, as you see the UPF here. You can then insert mobile edge compute. So now what it can do is you can run applications. Instead of running all the way from the cloud, you can actually have the application sitting right inside that factory. And the other part to this first option is you can run majority of the control plane function of 5G outside of this enterprise location. So you don't have to put everything on on premise. The second iteration is a little bit different where, yeah, in some cases, maybe this is a mining site, which, potentially have, connectivity challenges. Like it might not, sometimes the link to the outside world might go down. In that case, they would demand to run the entire 5G core on-prem, as illustrated by this bottom example. So we're seeing this because we're seeing a lot of enterprise have interest in building this solution. Actually, a lot of them are looking to do it on their own as well. So especially in US where you have the government driving initiatives such as the CBRS, the Community Broadband Spectrum, and it becomes very easy for enterprise to just sign up for a piece of that spectrum and then just run their own private network. But this is not something easy to do because enterprise definitely needs support on wireless network design, which is a very specific skill. They also need someone with expertise to manage and operate the network. And if you can imagine, if we're talking about running applications on-prem, you also need to find the right partner to support deployment and operation of these applications as well. So from our perspective, this is a pretty interesting example which we just did very recently on private network. So this is a collaboration with Carnegie Mellon University in the US, together with a network vendor partner, Federated Wireless. We also have Mac Computing, who actually provides us with a safe distancing video analytics software. So if you look at this particular use case, we basically have a university campus, and they want to implement a safe distancing solution, and they want to use wireless cameras for that because they don't, it's hard to roll out cameras that are wired across the campus. So the problem space is actually how can we implement complete wireless cameras and then use those cameras to implement a safe distancing analytics solution, such that we can generate real-time alerts and do things like facial recognition. So the key building block for the solution is obviously that on private network solution. So this is a radio access network, mobile core network, network management from Federated Wireless. We also need a platform to run those components on-prem. So this is where AWS Snow, which we will also dive deeper into in the next session, becomes a very compact platform you can deploy on-prem to host these functions. And then to enable the actual video analytics solution, in this particular case, we use the AWS region. So we support an inference instance, which is called F1, and we use that to run the Mac Computing video analytics solution. So what you can see on the diagram is across the campus actually have both indoor and outdoor locations. These locations are now equipped with wireless cameras, and then they are connected to the radio network, which provides 5G coverage across the campus. And then these are connected to the core, which are hosted onto this AWS Snow platform. And then the analytics, the video analytics application are actually running inside the region. So the end result is a fully wireless video analytics solution. So if we detect things like a lot of students are gathering in the same hall, it will trigger an event, and a safe distancing officer may come in. And this is just one example use case. The university is planning to use this foundation to implement more use cases like AR, VR, immersive learning, and and other use cases as well. For this next section, we want to spend some time and share with you holistically some of the key enabling services that enables those 5G and edge computing use cases we shared them earlier. There's a lot to cover, so this is not meant to be a very, very deep dive into every single service, but rather we want to give you an introduction, get you a basic level of understanding, and then we'll provide you with some resource so that you can read up on those services later on and get inspired for your hackathon. So the first thing we want to start off with is based on our observation, we see that most real-world commercial applications will not be edge only. So what that means is we expect there will be a lot of applications that continues to have some parts sitting in the cloud and then some parts sitting on the edge. And the reason why that is important is because of this concept of application continuum. So today we are already supporting thousands and hundreds of thousands of customers and their applications, be it enterprise or business or web application. We are already supporting those applications running in our AWS region, which is centralized, and it's available in 24 global locations, and that has actually enabled a very rich ecosystem of developers and SI and software ISVs to come up with great sort of best practice architecture patterns, the tooling approach, and all those things to make the deployment of workloads on cloud very easy. At the same time, we also acknowledge that there continues to be a lot of workload that needs to stay on-prem. One reason is data residency or regulatory requirements that unique to specific country, or contractual obligations for specific enterprise or industry vertical. And of course, very relevant to this particular conversation is the requirement to run workloads on premise to support things like local data processing. So you might have video or media content that needs to be transcoded and cached on-prem, which makes perfect sense. Or you have applications that have lots of data that cannot be easily moved in and out of the on-prem environment. So again, that will be a candidate to your process locally. At the same time, we're seeing an emerging wave of low latency enabled immersive experience, such as augmented reality, virtual reality, or if you're implementing like a closed loop control solution for a factory, that actually requires very low latency. So again, those are workloads for low latency, localized on-premise processing. And what we're trying to highlight in this case is it's actually quite hard to run workloads on-prem, because the more endpoints there are, the more endpoints you need to manage. And then a lot of these endpoints are heterogeneous. So they come in different shape or form, different vendors, different flavors of hardware and software stack. So the complexity of deploying and managing, edge workload is actually, quite high. When we speak to our customer, they have consistently feedback to us that, we enjoy AWS Cloud. It's a great experience. We get a lot of business benefit from it. What we actually want also is, can you actually bring that cloud experience to, to our on-premise location? Because we still have these workload that needs to run on-prem. So what customer have demand, and we have listened to them very closely, is they want the same reliable, secure, high-performance infrastructure that really sort of symbolize the experience on cloud, and they want that on-prem. They also want the same operation approach and same tools that they're using in the cloud, and they want to expand that to on-premise environment. At the same time, they've been enjoying, the sort of on-demand consumption of cloud services, the API-driven programming model, and they want that also to be extended. And also not to be overlooked the whole tooling, automation, deployment, securities, which they have enjoyed in the cloud. They want, again, to be able to expand and take that into any hybrid on-prem environment. And then the last one is also important, is they've seen a lot of the great use cases, business outcome, and how it drives innovation in the cloud. So they really want the same outcome, to be able to kind of make those available in an on-prem environment. So to address this particular customer need, we have introduced a service called AWS Outpost about 18 plus months ago. And what AWS Outpost is really extending AWS infrastructure and service on premise. So that means this is AWS design infrastructure. We have an implementation called the Nitro infrastructure, which is based on our own innovation. It delivers a very lightweight hypervisor layer with some very optimized approach towards networking, storage and security offload. And this is essentially an AWS experience that we manage and update as part of the AWS region. So what you can see on the right-hand side is basically an AWS Outpost rack that customer can choose what kind of capacity or what kind of compute processing or storage to be included. And then we will package it up, it will ship it to a location of your choice, and we will operate on your behalf. So we become sort of the single point of service and support. So this is a very important enabler for a lot of these, edge and latency sensitive use case, because what we are enabling is the same AWS programming model, the same AWS cloud services, but it is now available on premise. And currently AWS Outpost is available in a sort of full rack 42U form factor. Which is the current version available on the market. We've also listened to our customers' feedback, and they also want the flexibility and the experience of AWS Outpost, but they want to deploy it in locations which have space or power constraint. So late last year during reInvent, we've introduced the launch of two new form factors, the 1U and the 2U form factor as shown here. So again, this offers the same AWS infrastructure service experience, but it comes in a smaller form factor. And this actually enables some very interesting possibility. So for example, in the telco networking space, having this small form factor platform actually allow us to start exploring how we can use these platforms to support things like open RAN or virtualized RAN, and how can we take these platforms and distribute it in let's say radio access network next to cell tower kind of environment. So to kind of visualize the notion of how we are offering AWS service locally on Outpost, this is a high-level summary of some of the key services that are currently available on Outpost. So you will see, if you have experience with AWS Cloud, you will see some very familiar services like Amazon EC2, which is our compute offering, Amazon EBS, which is our block storage offering, things like ECS, EKS, which is our container service offering. And then we're also offering implementation of relational database RDS and object storage S3, plus things like load balancer, which is very important to help front end and steer traffic in and out of Outposts. And then obviously all the other key capabilities like monitoring and compliance certifications to on-premise environment. In the context of this conversation about 5G edge use case, AWS Outpost actually unlocks some very interesting new opportunities. So this is a very, what I'm showing you, this example is a very recent, effort we have, kind of developed together with Verizon Network in the US. So what this is we're partnered with Verizon. So Verizon is actually providing their private 5G network, and they have leveraged AWS Outpost as a private mobile edge computing platform. So you were seeing in some of the launch press release, they're actually offering this to companies like Corning, which is like a major fiber cable manufacturer. So the challenge for companies like Corning is today they have factory floors that it expands through a very vast floor space, and they want to pursue digital transformation and automation inside that very large factory. And the way they do that is by basically introducing robotics, autonomous robotics into those factory floor and production line environment. So one of the key things they're looking for is, well, how can they easily automate the operation of those robots? How can they actually provide like a wireless environment to enable those robots? And can they actually, without going through like a bespoke development of those capabilities, can they consume things like robotics as a service? So the solution, we have developed together with Verizon is using Verizon's 5G covering the factory floor. We partner with, robotic solutions provider so that they can provide things like, autonomous navigation and sensing as a service by using AWS Outposts on premise connected to the 5G network. So this architecture you're looking at is the AWS Outpost is actually sitting inside the factory floor, and inside the AWS Outpost we're running, the 4G or 5G mobile core that connects to the private radio network. And then we are also enabling things like computer vision application or other industrial applications to run locally on Outpost to deliver that low latency experience. The application running on Outpost is then interacting with, the autonomous guided vehicle, the robots that are roaming around the factory floor. It's supporting, video cameras that are mounted on these robots, as well as other static cameras deployed across the floor, and then also other sensor equipment, and using that to support things like predictive maintenance use case. And what you also notice as part of this solution is there are also workloads that are not as latency sensitive, and these are the ones that are being centralized in the region. So we don't need to deploy them to consume like the valuable resource out on distributed outposts. So the business outcome is using this package solution. We actually enable your companies like Corning to offload some of the processing capabilities to the edge, and just overall just make it a lot easier to deploy. So you can imagine there's a lot of repeatability of this use case, not just in with like industry manufacturer floors. There's also other very similar scenarios, like it could be energy company, it could be mining company that will have similar requirement. The next service we'll talk about, as we highlighted before, AWS Wavelength is a very specific service that we are delivering together with our telco partners, especially 5G telco partners. And its main objective is to really make AWS compute available as close to the 5G user and the application and device as possible. So some of the benefits about this application continuum, it also applies to AWS Wavelength. So for example, it is still an AWS service, so customer and developers do get that AWS developer experience. And at the same time, because it's connected to the 5G network, as more device becomes 5G enabled, we can actually make the low latency cloud services available to more and more endpoints and different types of device and users. So the best way to visualize what Wavelength is look at like how it fits into a telco service provider's architecture. If we start on the right-hand side of this diagram, this is the 5G mobile device connecting to a 5G mobile network. And what you see on the left is the AWS region. So in the past, applications are hosted in AWS region. And you can see that between applications that are in region versus the endpoint, which are these user device and mobile terminals, that latency could be in tens of milliseconds, or in some cases could be 100 or more milliseconds. By pushing out AWS cloud into the telco operators 5G network, we create these wavelength zone as described on this diagram. What it means is now you can actually run some part of that application in wavelength zone and significantly reduce latency to the end user applications. And then there's also a benefit of, now that you're doing processing here, you can actually reduce or minimize the amount of traffic you need to send all the way back to the region for processing. And then one additional point is, because this is an extension of AWS Cloud Experience, we also understand that customers or developers will continue to have a need to access services, cloud services in the AWS region. So through a construct called service link, we just say secured tunnel between wavelength zone and AWS region. We can actually allow very seamless and easy access of any AWS services sitting here. So if you have workload running in the wavelength zone and it needs access to AWS service in region, it can do so through this service link. So just to kind of even describe this even more, here's an example edge application architecture that is deployed in AWS Wavelength Zone. So this is courtesy of the Verizon Edge engineering team. So they've been fantastic. They have actually kind of shared this information publicly on their 5G Edge blog. So what they have done is they have, since they now have access to Wavelength Zone in the US, they've been exploring, well, how can we make use of it? So the first application they've written is this reverse geocoded application. So at a very high level, think of this as an application tag that is taking input coordinates, your longitude, latitude coordinates, and then convert it into a physical address. As you can imagine, we are having more and more self-driving cars and autonomous drones that are out there. So those devices will be able to pick up the coordinates, but they need to have a environmental location awareness of their whereabouts. And this is where this reverse geocoded application becomes very useful. By deploying it to the edge, it can actually significantly reduce the response time to support these queries coming from these autonomous devices. So what the Verizon team have done is to kind of look at the overall application architecture, and they've decided that some part of this application will definitely benefit from sitting on the edge, which is on the wavelength zone. And then they've also decided that there are other parts of the application which can easily stay in the region, so they don't need to be distributed. What's more interesting is, because the experience is an extension of the AWS cloud, so what that means is, whether it's in wavelength zone or in the AWS region, they can enjoy the same, Amazon managed Kubernetes services as we illustrate here, right? And then, so from a user perspective, if the end user connects to the Verizon 5G network, those devices can now interact with workloads running in wavelength zone through the carrier gateway construct. There's also cases where these workload for this application, they might need to store some storage into the cloud, and this is how we illustrate here. They can actually use a gateway endpoint in order to access the Amazon S3 object storage that is inside the region. So the key learning they have, and they've sort of made this as a suggestion to people who are thinking of developing edge application, is really think about your application architecture. If the part of the application is non-latency sensitive, you can feel free to keep it in the region. And here's some examples like master database and authentication function, which are not latency sensitive. And then there are really latency sensitive modules or part of the workload that should would benefit from sitting on the edge. And these are things like real-time computations or data sets that are specific to a particular region, right? So that's sort of their advice, and I hope this will be something useful for you when you consider your application architecture for the edge use case. So beyond AWS Outpost and AWS Wavelength, I mean those are fairly substantial infrastructure. We've also developed AWS Snow family. So the use case for AWS Snow family started from data movement. We used to have customer trying to migrate to the cloud. They have a lot of data they kept on-prem, and they want to move that into the cloud as part of their cloud migration effort. And for a lot of those customers, they might not always have high-speed network connectivity to their on-premise location. So we have initially come up with the Snow family with flavors like Snowball, Snowball Edge, even AWS Snow Mobile. These are essentially storage platform that we ship to the on-prem location. We will ask the customer to run a backup and storage process, and then we will ask them to ship it back to us, and we will then be able to import their data into their cloud AWS environment. So that was the original use case. As I said, we even have AWS Snow Mobile, which is basically a very, very large scale storage platform on wheels. So we can actually take it out to customer site and ship their data back, right? And over time, we've listened to our customer. They've said that data movement use case is great, but I also need use case where I'm actually doing edge compute processing on site. So this is why we have been, introducing new capabilities to the Snow family, and use that to enable like edge local processing capabilities. So platforms such as AWS Snowball Edge and AWS Snowcone are actually devices you can put out into the field. They can operate in what we consider disconnected or like environment that are not really data center, so they can operate in like very harsh environment as well. And they are basically our way of extending AWS capabilities to kind of non-traditional. And if you think of what these environments are, I mean, here's some examples, right? I mean, this is a mixture of non-profit organization going out to some very harsh rural areas to perform their mission. Military mission, again, could happen anywhere. It could be an industrial site, and so on, or it could be and in this case it could be like a video encoding use case but out into the field. So what's common in all this scenario is these are non-traditional data center environments, so you cannot expect like the adequate sort of power or cooling or anything like that. And that's why the platform you're seeing, these are actually all AWS Snowcone shown on this picture. And then these ones in the middle are AWS Snowball Edge, right? So what you're seeing is these platforms are actually enclosed in like ruggedized casing. They are rain and dust resistant. They can operate in disconnected mode because when you look at these locations, a lot of them would not have reliable continuous network connectivity. So the point of these platforms is to be able to survive those locations. So what we have is these ruggedized rain and dust resistant platform that can operate in disconnected fashion. It depending on the flavor you choose, we can support like 40 terabyte to 100 terabyte storage locally. You can actually deploy Amazon machine image to these platform, and also run like containers on these platform. And then the overall experience is still managed by like the broader AWS management and operation tools. So it's essentially extending that seamless AWS environment and operation capabilities out into this distributed edge. To put into context what the actual use case are in a 5G and edge discussion, this is the architecture showing a remote robotics use case. This is in fact the underlying architecture of the the Ghost Robotics video example you saw from the beginning, right? So here, their problem is the Ghost Robotic robots. They need to be deployed in all sorts of remote and dangerous locations. I mean, these are locations where you don't want to send humans, so you want to send robots instead. And the robot needs to perform some very data intensive tasks. It needs to do real time and video analytics because it's kind of the eyes and the grounds. It needs to perform mechanical tasks, so you need to do real time remote robotics control. So you can imagine there will be a remote operator trying to control the actions of this robot. And then, of course, what it means is as it goes through these harsh locations, it will not have reliable network connectivity. So that means there has to be a network solution, like local network solution, to overcome that problem. So that's why we've been working very closely with Ghost Robotics and other network vendors and software vendors. Essentially, the solution is to, on the robot itself, it will be equipped with like radio antennas and mobile core. So think of this as almost like a cell tower, on wheels or on legs, right? So this will enable on-demand mesh network on the robot itself. So as the robot moves around, it can form mesh network with other robots so they can talk and interact with each other. It will also be able to make itself available as an access point so that other adjacent device can interact with it. And of course, what it also means is if you have a remote control crew that is a little bit of a distance away from the robot, it can still control the actions of the robot via this local network connectivity. And in addition to that, there are other workloads that doesn't need to sit on the robot. They can sit in the region and support the robot, if and when it has connectivity to it. So the end result is this package offering using a platform like AWS Snow. I mean, all those things I talked about before, all those functions are actually hosted on AWS Snow. So you can imagine using AWS Snow and package with these, onboard radio network and mobile core capabilities. We actually greatly simplify the setup process, and we actually greatly simplify how complex it is to deploy a local network. And we actually enable more scenarios for these robots to be deployed. On from that infrastructure-focused conversation, the other very important part of the solution is IoT capabilities. So when we talk about IoT, when we think about IoT, we often think of it in this sort of virtuous cycle, right? Where it starts from your edge and devices. So that means your IoT sensors, your microcontrollers, any edge device you need to implement out there. I mean, we've already talked about a few like Outpost, Wavelength, and so on, and Snowball. This is the foundation of your IoT solution. These are the endpoints that are actually collecting, generating data, getting insights. And then, to manage all these sensors out there and to aggregate and collect data, that's where you need like the connectivity and control services. So in our case, you hear in the next couple of slides, we have AWS IoT Core and things like IoT device management. These are capabilities we have built as an IoT backend to enable large scale deployment of IoT endpoints. And then once that scaled foundation is established, we can then think of, well, how can we extract insights from these data collect from sensors? Well, this is where you have like the analytics service and machine learning and AI services. So examples specific to IoT would be something like IoT Sitewise and the suite of AWS purpose-built data store, Amazon SageMaker, which is our end-to-end machine learning service, that's also going to play an important role. And one thing we've done recently is also turn our focus to enable industry-specific use case. So all these things are great building blocks for customer to build solution upon, but we have put in some effort to build some specific capabilities for like video analytics or predictive maintenance for manufacturing. So we build those off-the-shelf managed AI service so you can consume right away without being a machine learning expert at all. So let's kind of look at some of the key IoT capabilities. And the first one we start with is FreeRTOS. So FreeRTOS is essentially the #1 microcontroller operating system on the market. It is basically collection of kernels and software libraries that you can implement on microcontrollers, which are found in many of the IoT sensor devices out there. So customers have been demanding they need a consistent, secure, high quality operating system that they can trust and deploy on these microcontroller devices. And they've outlined some key capability they need, which is supported by FreeRTOS. So the first one is local connectivity. As we have spoken quite a few times, in these edge use cases, you're not going to always get reliable connectivity to the cloud. So the ability to support local connectivity is important. And with FreeRTOS, you can connect FreeRTOS enable microcontroller to edge IoT gateway devices running AWS IoT Greengrass. And you don't need a cloud connection for that. That connectivity can be done locally. And then the second one is if and when you have cloud connectivity, you can basically collect and push the data you collect from the sensors and push it back into the AWS IoT core cloud backend. So in order for further processing or to take actions. So this is a very seamless way of both integrating locally and then integrating back to the cloud. And of course, you need to make sure that these microcontrollers are secure, data is encrypted, and because they are deployed in a very distributed fashion, and you will always want to maintain a secure baseline operation environment, you need to do things like over-the-air updates, bug fixes, and code signing. One of the recent additions to FreeRTOS is our long-term support. So again, because customer wants consistent, secure, reliable kind of experience on these operating systems, so they demand long-term support, which we are now offering to our customers. And last but not least is to really enable that ecosystem innovation and also to address customers' security and compliance requirement. We have FreeRTOS is open source, right? We've been working with the community to really sort of drive innovation within that open source ecosystem. If we go up the stack, then we talk about AWS IoT Greengrass. So what AWS IoT Greengrass is pushing AWS cloud capability out to the edge. And what under the hood, what Greengrass actually enable is it allow us to kind of bring some of these AWS cloud capabilities in and run them locally so that it can interact with IoT sensors and device locally. And there's many use cases, related to security and related to latency requirement, related to the nature of the use case, why you need to do that, right? And the key capabilities of AWS IoT Greengrass include things like the ability to run machine learning inference. So we can actually push out we can train machine learning model in the cloud, and then we can actually push that out and run it on edge IoT gateway. So we can do things like localized video analytics or localized closed loop anomaly detection and so on. The second one is connectors, and this is important because when you deploy an edge IoT gateway out to the field, chances are, this edge IoT gateway might interact with many other third-party devices or services. So it could be other third-party IoT services or other device thing on-prem or other AWS cloud services. So the point is having these connectors with pre-built support will allow us to really expand the IoT ecosystem that we can enable. And then the other thing will be the secrets manager. So again, this is like foundational security capabilities that we need to enable. We need to make sure that the IoT data is being processed in a secure environment. Container support is a very important capability. So we've now introduced the ability to do AWS Lambda and also deploy Docker images or a combination of both. So you can develop your code. You can leverage code you develop from the cloud, but you can push the execution of those code locally onto AWS IoT Greengrass. And then the last one is in many IoT use cases, we need to deal with a high volume of data streams. We need to process those. So with the stream manager capability, we can now actually handle and process and export high volume data stream that we collect from edge devices. The other thing that is we're very, very constantly looking at is how can we improve the Greengrass experience further. And one of the things that customers have asked us to do is, well, we like Greengrass, but can you make it more lightweight? Because we have constraints in some of our IoT gateways in terms of compute processing or memory capacity. So we have listened to that, and we have in Greengrass 2.0, what we've done is make Greengrass modular. So now you can selectively choose different feature sets or modules to be deployed, and as a result, actually really optimize the footprint of Greengrass running on Edge IoT Gateway. Another key feature is the ability to deploy device software at scale. So with things like static or dynamic things group, you can actually sort of group different types of device of different nature together and apply different software deployment policies and strategies so that you can manage like lots and lots of device at scale, but use like policies to kind of still maintain a granular control. And then the last, sort of enhancement we've introduced in Greengrass 2.0 is the ability to, for developers to interact with Greengrass locally. So now we have introduced a Greengrass command line interface where you can actually, do your localized development interacting with those IoT gateways directly. And last but not least is, we made IoT Greengrass open source as well. So again, we fully embrace the power of innovating together with the community. Moving up the stack is the AWS IoT Core. So, now that you have your sensors, you have your Edge IoT Gateway to aggregate and to support localized processing, you need a very scalable backend service to manage these devices and gateways at very large scale. So the key capability of IoT Core include identity service. This is essentially the ability for us to do things like certificate management, automated registration, and be able to handle like a large number of devices. Device gateway. This is a key capability. This is how we actually support the various types of IoT protocol, different types of connectivity, whether it's MQTTs, WebSocket, HTTPS, and we have been leveraging this capability to deal with like the heterogeneous communications protocol that we've seen in IoT device and endpoints. Message broker, you can do two-way message broker. You can do pub sub, between device and application. So again, instead of building or running your own message broker service, you can now leverage this from IoT Core. Rules engine is an important one. This is where we can actually control the flow of data to various AWS service endpoints. So for example, we can select certain stream of data and pass it to NoSQL database, or we can select different stream of data and pass it to like data warehouse like Redshift, or we can even enrich the data by combining raw data we collect from sensors with like a prediction outcome from SageMaker, and just enrich that data and make it more contextual. Device shadow is a very interesting concept. Essentially, this is a cloud representation of an IoT device state. So what how this can help is you can actually use this to drive programmable outcome, right? You can set what is the desired state of this device versus the actual state, and if the device actual and desired state doesn't match, then here's some actions you will trigger. And then the last one is registry. So essentially, this is a way to kind of catalog the AWS device for consumption by other AWS services. So you can group, all the, let's say, connected vehicle in one group, and then all the autonomous drones in another. And then you can actually query, these devices very easily. For example, like show me all the devices that were connected, for the last 7 days, or any queries of that nature, right? So the easiest way to understand how this all comes together is using a real example. So what we're showing you is a connected vehicle example, and in the context of these edge use case, this is actually quite relevant. So you can imagine when we say connected vehicles, there's actually a lot of sensors and cameras on board of the vehicle, and one thing which is also important is in the real world, for connected vehicle to function properly, it actually needs localized processing capabilities. Like you cannot always rely on control or signals coming from cloud, right? So what you can see here is, on the vehicle itself, there are many different sensors, and we can actually run AWS IoT Greengrass as an edge IoT gateway inside the vehicle. And using Greengrass, we can enable things like a local message broker to facilitate communication between device and endpoints and sensors. We can obviously use it to enable that localized secure environment. We can run machine learning inference locally. So, train up a model and push it out and run on IoT Greengrass. And then you can also run pieces of code like, a local Lambda. And you can, also, enable like local device shadow. And then from a end-to-end perspective, the IoT Greengrass will also maintain synchronization with AWS IoT Core. So this is kind of an end-to-end approach of how you can aggregate, process data locally, maintain the synchronization with the core. And then if you zoom into one specific scenario, let's take this example of, we want to detect in real time distracted driver. We also want to detect traffic signs. So what this is showing is that you have your sensors on the vehicle. This can be telemetry data you collect from different parts of the vehicle. You can also have sensors running free RTOS. You can have like smart cameras, for example, deep lens camera. The data from these is aggregated and collected by Greengrass. We would have train up models, machine learning models using Amazon SageMaker, or if you prefer to kind of DIY, you can use some of our deep learning machine images. But that train model will basically, equip us with a way to detect, well, is the driver, pulling out his mobile phone, or is he getting distracted? And that train model can be pushed out to Greengrass for local inference and processing. And then whenever there's connectivity, that will also serve as a way for us to complete this feedback loop, so that we can take feedback and constantly enhance and improve the accuracy of this model. We've talked about the edge cloud infrastructure. We've talked about IoT service. Next, we're going to talk a little bit about machine learning. So this is like a very comprehensive depiction of the full AWS machine learning stack. We definitely do not have time to go through this in detail. Where we want to point your attention is, this machine learning stack is really catering for all types of users, right? If you are the hardcore machine learning data scientist, you can feel free to choose your own framework and then leverage any of these underlying building blocks and fine tune it for your machine learning development pipeline. If you don't want to do all the heavy lifting by yourself, you can leverage Amazon SageMaker, which is becoming a real end-to-end platform, from preparation of data to labeling of data to training of machine learning model to deployment and management and operation of those machine learning models. And one thing we actually add and we talk about it is, how do we manage these models for edge devices, because they are becoming more and more important. And then the top part is really where, if you do not have AI ML expertise, but you still want to use AI ML, then these are off-the-shelf pre-built capabilities you can use right away. And specific to our discussion, there are capabilities like these industrial AI services, which we'll share a little bit more later. And these can really be applicable for edge use case without the customers being a machine learning expert at all. So if we start by zooming into, how can we enable machine learning deployment for the edge? One of the foremost requirement is, well, today, if you have experience with machine learning development, you appreciate the process of building your own model, by choosing one of these framework and then optimizing that model for a specific deployment environment. That's a difficult and challenging process. In the context of edge, you potentially have lots of different endpoints you need to deal with, which actually compounds the complexity of distributing and deploying machine learning model to the edge. So what SageMaker Neo aims to achieve is, we already have a very wide variety of machine learning model framework support, as shown on the left here. These are already supported by SageMaker. And we know there are these endpoints, different types of OS and different types of CPU architecture. SageMaker Neo will automate the process of taking the models you develop and then converting it and optimizing it and fine-tuning it for these different deployment endpoints. So what we aim to do is kind of make this whole flow of edge machine learning model development a lot easier. And as an end result, we actually help you get much better performance, because your model will be much more optimized for each of these environments. And you can imagine the speed of innovation going from the model to these edge environments also greatly improved. And it's not just the model optimization that's important. Like, once you have the model optimized and you have chosen to deploy the model using any of the AWS tools available, for example, IoT Greengrass can be one way of deploying those models onto the edge. After you've deployed, you actually need to operate and manage those models. And the reason why you do that is, you need to continuously monitor the model performance and use that feedback to enhance your model to improve the accuracy of those models. At the same time, you might have cases where you are actually running multiple models concurrently on like a fleet of edge device, right? So you basically need a way to operate and manage and update these models on an ongoing basis. And this is where Amazon SageMaker Edge Manager comes into the picture. So you can imagine between SageMaker Neo, which does the model optimization for edge endpoints, and IoT Greengrass, which can help you deploy models to the edge, and SageMaker Edge Manager, which can help you kind of operate and update the models. You actually have an end-to-end approach to manage machine learning deployment on the edge. And then the next area is industrial AI. So these are essentially services based on our own interaction with customers and experience. We reckon these are going to really help our customer get started very quickly. I will talk about these in more detail on the next couple of slides, but at a high level, video analytics for the edge is very, very important use case. We've seen it across many industry. Predictive maintenance is another very important use case. Again, we've seen it across many heavy industry. So customer wants to have an easy, quick way to implement predictive maintenance using machine learning. And then obviously the other one is like supply chain quality assurance. Again, this is another managed AI services, which I'll talk about in more detail in the next couple of slides. The first one is AWS Lookout for equipment. So this is still a service in preview, but at a high level, what this is trying to address is today across many heavy industry, you have customers invested in machinery. A lot of those machinery already comes with sensors which can detect things like temperature, vibration, pressure, all sorts of physical metrics. So with Lookout for equipment, what we can do is actually ingest data from those sensors that are already on board the equipment and the machinery, and then use those sensor data to feed that into a custom machine learning model. So what we can do is over a period of time, we can actually establish the baseline, the steady state of those machinery or asset, and then we can derive things like operational relationship between different sensors on each asset. So we can kind of correlate between what the temperature versus the pressure, and kind of correlate their relationship. And then as a result, what we can do is, if we detect anything that is deviated from the baseline or the steady state or the healthy state, then it gives us the indication to alert end users or other operation staff. And this could be the asset management staff or the operation officer in any factory, right? So this is a way for customer to get started with machine learning. They don't need to actually program or code any of the model. They can just use it, and they can get started with machine learning and leverage it for a predictive maintenance use case. The other service is Amazon Monitron. So this is again trying to address that predictive maintenance use case, but it's an end-to-end solution. So that means you will have customers that have those machinery, but they don't have any sensors. In this case, we are actually providing the sensors as an end-to-end solution. So as you can see, these are like example of what they look like. And they're very easy to use and very easy to install. So as soon as the technician installing these sensors on the equipment, and right away you can start collecting data. And then with those data you collect, we can actually compare to a machine learning determined baseline, or we can compare to other industrial standard like an ISO standard. And obviously, we once these are implemented, we can leverage continuous feedback to improve the performance of the model. We can push out over the top, over the air update to these sensor devices. So an example customer that are already benefit from this is Fender. So this is a very large musical instrument producer. So they have been leveraging Amazon Monitron to monitor the machinery in their production line, and what they managed to do is using that to do predictive maintenance or predictive repairs of any of the machine they have, and as a result, they actually avoid downtime, right? So you can imagine if the piece of machine is down, the whole production line may be impacted. So using predictive maintenance, they actually avoid that. Another industrial AI service is AWS Lookout for Vision. So similar to the machine, the predictive maintenance use case, again, this is a managed AI service. What it does is it's actually collecting data from like sensors or cameras that we implement on site, and use that to basically detect you know deviation or defect. So one example is the camera might be taking a snapshot of a production line, and then it's taking the capture of what a normal production line would look like, the input and the output. And then by comparing the imagery taken, we can really quickly determine, well, if there's something that is deviating from the baseline, right? And usually this task in a normal production line is done by human. So that means you need some humans to do that ongoing inspection, and so on. The industrial AI service is Lookout for Vision. So this is specifically focused on how can we automate and use machine learning to drive that defect detection, right? So imagine you're in a factory line, you're taking a image snapshot of the normal factory line. So you're comparing, what the output would normally look like. And then in real time, based on the image you're capturing, we can analyze and we can detect if, the output deviates from the steady state or the normal state, right? Today, a lot of this quality assurance defect detection is done by human. So you need human to detect. And the problem with that is it's not consistent, it might not be accurate, and it's a very manual-driven process. So using Lookout for Vision, we can actually kind of automate that whole inspection quality assurance process. And again, no machine learning expertise required. And then the last one I will cover for this part is the the Panorama solution. So we have many customers that are coming to us, and they said they have already invested into many on-site cameras. Maybe they implement those cameras a couple of years ago, and now they want to leverage AI, ML, and do like edge video inference, right? So in the past, one thing which is a common pain point for a lot of customers is they have to send a lot of these video streams to the cloud or a centralized data aggregation point. The video stream can get very large, and then it's just very difficult and gets expensive in terms of introducing those smart video analytics capabilities. We have then introduced AWS Panorama appliance. Essentially, this is a machine learning appliance that you can implement on the edge, and you can connect this to multiple cameras in parallel and use it to drive very highly accurate computer vision model. So you can run the computer vision model locally at very low latency. It can be your own model you have already written, or it could be like a partner application, and you can use it to detect things like PPE detection, very important these days, social distancing monitoring, or you can detect specific objects. Panorama appliance is a physical appliance you can implement on site. We're also making available the Panorama device SDK, which is going to be still in preview mode. Using that, what we can do is we can implement where we can encourage an ecosystem of partners and device maker to leverage this particular SDK, so that there will be a consistent environment to develop and deploy video analytics application and machine learning model on the edge. So we've been working with lots of ecosystem partners to encourage them to leverage this, and drive that API adoption. And we are working with some very large partners like NVIDIA, as shown here. So you expect to see a variety of devices coming to the market that supports the Panorama device SDK, in the following months. And then just if you're interested to understand a little bit more how Panorama actually works in reality, feel free to look at this blog post. I mean, it actually depicts a very interesting problem, which is a parking lot car counter application. So this blog actually describes how we have implemented. It's more of an experimental use case of using computer vision to detect how many vacancies are there in the car park. There's actually use cases where you're not just looking at a single car park, but many car park owners actually have multiple car parks in the same city center. So what they can do is by aggregating this information in real time, you can actually redirect people to the next car park to kind of offload the congestion. And then there's also a lot more other outcomes, like we not only you can count the number of cars, we can also check if people are properly parked inside the lot. So there's a lot of possibilities we can enable using computer vision on the edge. So the last capability we'll talk about is AWS RoboMaker. So unfortunately, given the time constraint, we won't be able to go very deep into this. But in a nutshell, you will have seen the importance of robotics in all kinds of 5G edge use case. We've already talked about a few of them. Today, there is quite a few challenges when it comes to building robotics solution. Obviously, robotics solution now has to work with many other services. It's got significant touch point with machine learning, with video, speech recognition. So there's many other AWS services that it needs to interact with. So we have actually put in a lot of effort into enhancing AWS RoboMaker so that it extends and integrates very well with other AWS services. The second challenge is with robotics development, you don't often get to leverage or deploy onto real robots until later stage of that development cycle. So also, you need to kind of simulate interaction across multiple robots in many cases. So with RoboMaker, we have enabled a testing and training simulation environment on cloud so that you can, kind of leverage that simulation capability and make it a lot easier to develop your robotics solution. And then the last one is when you have built and test and train, you need to deploy. So this is where, again, it becomes a problem of how to deploy software to a large number of edge endpoints. And this is where, using AWS IoT Greengrass, we actually can enable scalable deployment of software to robotic endpoints. And one thing which is worth calling out is, especially where it relates to robotics, it's not just that we have helped our customer. We've actually been doing it ourselves, in fact, a lot. So when you look at Amazon globally, we have large number of fulfillment centers, and we are making the effort of investing and enabling a lot of those to be robotic fulfillment centers. Inside each of those robotic fulfillment centers, there are thousands, actually, of robots operating autonomously. So that experience we've gained actually help us really enhance and improve and really drive adoption of this service. So if you are interested, take a look at the link here. It's got some very interesting data points and use cases of what we're doing inside that environment, right? And I'll just leave you with a snippet of sort of a peek view into that fulfillment center. So this is one of our fulfillment center. And what you will see is that, there's all these autonomous robots. They are self-navigating, self-coordinating. Again, you wouldn't see a lot of humans in that environment, but they're basically the whole process of packing and also maneuvering from a customer order. This is fully automated, and you can see the space is huge, right? So imagine operation at that scale. You really couldn't do without the right type of robotics automation. This upcoming section, we want to share with you some of our learnings and observations along the way on the market realities around 5G and edge computing use case. The first observation is it's going to take a lot of people and different parties involved to truly incubate and drive maturity into the 5G edge computing ecosystem. If you look at this depiction of sort of a current edge computing landscape, what stood out right away is just the sheer amount of companies involved. So every one of these icons represent either a startup or a large enterprise or a service provider that claims to have involvement in the edge computing space. They either have a product or solution idea, or they provide some sort of related service to enable edge computing. And they range from device maker, people who make AR, VR glasses, communication providers, so telco who are offering 5G services, or application developers, so people who write video analytics solutions that are very latency sensitive. Or it can be something that seems not related right away. It could be someone who actually owns real estate or the property rights to location where you can build cell towers, or it can also be people who focus on data analytics and how they can use location analytics and extract business insights. So the challenge with so many different parties involved, it creates complexity in the whole ecosystem. And if we contextualize this problem, so here we outline some example categories of ecosystem player. I mean, this is not an exhaustive list, but as you probably can see, these involve sort of the usual suspect of telcos and IoT and application ISVs, cloud providers, and so on. So the biggest problem we have today is because we're still fairly new to this whole cycle of 5G edge computing innovation. The business value is often very ambiguous. So that means there's some hypothesis like cloud gaming might be something that we can really enable through edge computing, but not everyone can come out with certainty, say, well, what is the size of the business? What is the rate of return for that business? So there's a level of experimentation, there's definitely a level of unknown. The second point to consider is edge computing may not be the only way to solve a problem. A very typical scenario is around video analytics. Like we can implement video analytics in many different ways. We can push the inference capabilities to do image recognition all the way to the camera, or we can actually push that intelligence and the inference capabilities a little bit back towards the network and support those real-time inference use case on edge computing locations from the network. Or in some cases where it's the latency requirement is not so great, we can actually do a lot of these capabilities and inference implementation in the cloud itself. So there's no right or wrong or single way to solve a problem. It actually needs a variety of technologies coming together, which actually brings us to the next point, which is a lot of partners and technologies needs to be involved. So if we recall one of the earlier slides we showed about the horizontal and vertical enablers, that's exactly what we try to highlight there, which is it takes some repeatable capabilities, some very use case specific capabilities coming together to form any different use case. And then, actually very specifically relate to, the hackathon initiative you're exploring is there might be use cases that looks great and makes perfect sense, but only in a very narrow sense. So, for example, an AR VR implementation for a multi-party interaction might make perfect sense for a specific office collaboration scenario, but it might not be something you can easily replicate to other industry. And then the other part is it will probably take a little bit of time for any of these things to mature. So the initial investment required will be quite significant. There might not be any promised return, so to speak. And the speed of innovation is also expected to kind of grow over a period of time, but just not it won't be like at full speed right away. And then the final one, which is a point we raised earlier in the presentation, is location. It's very important in the sense that we're not going to get nationwide 5G or millimeter indoor coverage everywhere right now. So that means the use case might work in some location, but it won't work as long as you go outside a certain factory or smart building. So that is also a very important consideration. And in summary, what we're trying to say is there are too many players involved. There won't be a single participant who can kind of drive or own the overall value chain. There's certainly going to be what we consider ecosystem movers and value aggregators. AWS definitely aspire to be one of those, together with our telco partners. Another, just to sort of drive home a little bit more on the previous point, is the phase evolution approach, where if you look at 5G rollout, it's not going to happen in a big bang manner. So all the advanced economies that have rolled out 5G, whether it's Japan, Korea, Australia, US, or China, they have been doing it in a very incremental sort of evolutionary kind of approach. So the initial rollout will be targeting specific metro areas, rolled out to some friendly trial customer, and then edge is kind of the number of edges might be very limited, and many operators focus on using 5G initially to do things like consumer broadband, so fixed wireless access. And then as they pick up steam, as they ready the rollout of 5G standalone core, they can now make it available to a broader set of locations around any country. And you start to see them roll out things like small cell and millimeter wave in certain spots. And then, as we also said before, private network is growing in importance. So again, you will see pockets of private dedicated network roll out for larger enterprise. So you might now be able to see something like, hey, for a certain university campus, you can run augmented reality for remote for immersive learning. And the third phase is the scale out phase. So this is where you start to see nationwide coverage, the spectrum situation, the strategy would have been more optimized. So more of the spectrum will be sort of steered towards actual 5G deployment. And the penetration rate with things like millimeter wave will improve. And then in terms of the number of edge location, that will also come along as well. So this is where you start to see some of these citywide use case. Like for example, connected car use case using enabled by the edge is useful only if you can actually support a fairly large geographical area, because the vehicle will move around. Some of these drone automation or control solution, again, will make more sense if it's able to cover a broader geographical area. So what we're essentially highlighting is when you design your use case or innovation idea, also think of the impact of phase evolution. Like what you try to achieve might not be available from day one to a majority of the population. So you need to plan it in phase as well alongside the 5G rollout. So we also want to follow up those observations with some sort of recommendations. on how you can go about discovering, qualifying, and developing your 5G edge use case. So these 9 categories of use cases are just based on some of the industry observation we had. What we see is across these use cases, there's a lot of diversity. So each of these segments have their own unique requirements, and there is no one size fit all, right? So you can't expect to come up with a disconnected edge solution, and it will be just copy and paste to all these industry. It won't. So there's no such thing as a one size fit all solution. What we recommend you to do is group your use case together, categorize them against these categories. I mean, you can always expand beyond these 9 for sure, but work with your customer. Like, go to the end customer who'll be using these solution, work with them, extract from them their actual requirement, and then on a category per category basis, build up that knowledge of what they actually need. So for example, if you talk to 5 customers from healthcare, chances are you're going to find some similarities. You will find some common horizontal enablers that actually can help all those 5 customers. And then you start to build more insights and focus on developing the right capabilities for each category of these use case. And you can also simply focus on sort of 3 areas for qualification. So whenever you go into a conversation with this end user, you can think of, well, is this very unique? Like, do I need 5G or edge computing to achieve this use case, or these things can already be done using current technology? If they're not so unique, maybe you won't want to waste your time on such use case. And then are there dependencies? So an AR/VR asset inspection use case is great, but then it also depends on availability of like very small form factor compact AR/VR glasses. Are those technology mature right now? So the technology dependencies cannot be overlooked. And then the other second criteria is repeatability. So this goes back to the niche use case scenario we talked about before. So some great use case, some very interesting technically on paper. How many other customers will actually need this? Can I repeat this 5 times? If it's not repeatable, then is it actually worthwhile doing it, or it's just too bespoke for us to focus on? And then monetization. So think very deeply from the beginning. What are the mechanisms you can use to charge and monetize the use case? Is it a subscription model? Do you charge per device, or do you charge per API transaction? What is the value proposition that you can actually bring in, and what are the proposition that partners are actually bringing in, right? So the reason why monetization is important is, in reality, most of the 5G edge use cases, like, they are interesting, they can be monetized, but the revenue potential of individual use case might be small. So that means you cannot justify rolling out 100 edge computing sites just because of a single use case. So you need to find synergies between them. And more importantly is we need to go about this in a fairly systematic fashion. So set up repeatable framework. Some of those we can talk about on the next slide, which will help you to collect, qualify, and then progress this use case idea. And then focus on building out these capabilities bit by bit. And this is kind of a pictorial representation of what we mean by working backwards from customer. So in AWS, we always work back from the customer. That means our product development, our solution idea starts from what the customer actually needs. So if you look at this chart from the right to the left, the end customer is the one who started this whole conversation. So what we want to do is have a ideation workshop from the customer, talk to them, capture their requirement, understand the pain points, understand the personas involved. A single company you talk to might have multiple personas. The finance person versus the procurement person or the operation staff, they all have different needs. And then from those conversations, start to capture the raw data and apply the use case qualification I mentioned in the previous slide, like the capability, repeatability, monetization, against what you collect. So you can certainly build out some of these qualification questionnaire. We have quite a few of those which we are happy to share offline in follow-up conversation. Which will these questions will ask kind of what are the dependencies between 5G and other related technologies? What are the key business outcome the customer is looking for? What are the experience they're looking for, and so on. So from that qualification, you can now turn the customer conversation and the raw data into actual use case, which you will categorize into different pools. So these four are just example of use case categorization. And every one of these, you can kind of populate the use case into a template where you look at, what are the actual capabilities needed to develop or support each one of the use case? Are there repeatable capabilities you can, kind of develop once and use it to service multiple use case? What is the go-to-market business model? And from that point on, you then start doing real work, which is the prototyping in POC. This is especially important because, as I said, the business value is fairly vague at this point in time. So most customer or partners will demand seeing the use case in action. And that prototyping process is a very important process to collect and fine-tune your implementation. And then the last bit is probably a bit more longer term, where there might be many ideas you capture along the way. You're probably not able to do all of them. So what you end up doing is implement sort of a product catalog, capture certain product release in phases. That's how you can make sure you can progressively, practically develop these 5G edge solution. So I hope what we shared earlier is relevant and help you establish some kind of mental model to navigate through your 5G edge computing innovation journey. And we want to conclude this part by showing you what we consider an innovation flywheel. In AWS, we love to use the flywheel as a way to articulate and brainstorm the impact of innovation. So what this is trying to show is, this whole 5G edge innovation will start from someone making the infrastructure and technology enabler investment. So people like ourselves who are investing into those edge technologies, our telco operators who are investing into 5G deployment and edge infrastructure as well, and this will lead to a level of early ecosystem adoption and some kind of early business model to emerge. For example, in a very large country like Philippines, you might have a couple factory owners who are starting to embrace and want to try the technology. And then as more factories or manufacturing companies actually sign up, you will see more clarity from the discussion with them, and you can actually use those learning to formulate better defined use cases. And the more of the ecosystem buying into that, the more easier we can use to drive things like supply chain readiness. So in practical terms, what it means is, if in the local market, system integrators start to see, hey, this connected 5G with 5G is becoming a trend and there's a business, they will start to invest. They will start to invest in capabilities. They will start to promote it more. The cost to things like edge platform or edge software will in turn decrease over time because of better economies of scale. So what it means is, all of a sudden, as the ecosystem grows, the cost to access these technology will reduce, and it will become more and more available. And it will eventually result in more value being generated in terms of business value to the end user. So more factory will benefit from the the result from industry automation or low latency autonomous control. So this has a sort of a compound effect. That's why we consider it as a flywheel. And in the context of what you're trying to do, you use this also as a mental model to think about not just the impact you can make right now, but kind of that innovation cycle you can trigger and drive over the medium to long term. So in addition to share with you, the use cases and the service overview, we also want to share with you a quick demo. Hopefully that will help you get your hands dirty, and you might be able to leverage the contents of this demo in your hackathon as well. So this demo is about running an open source 5G core network on AWS. So there's a project called Open 5GS. It's a great community. It used to be that 4G or 5G software is very proprietary. You can only get it from the large vendors. But over the last couple of years, we've seen, proliferation of, community coming together, people contributing and making the software available. So, our teams have actually written a blog on this. So most of the demo you saw is actually taken from the content of the blog. And at a very high level, I won't go into details of this architecture, but at a high level, what you see is the Open 5GS core is comprised of the control plane and the data plane elements. It also includes both the existing 4G core network function as well as the 5G unique components. So the green are the 4G components and the red are the 5G components. And because they have different performance characteristics, we're going to run the control plane functions on one server, and then we're going to run it on the data plane functions on another server. On top of that, to support end-to-end testing and development, Open 5GS will also work with a variety of, either real radio RF network components. So you can actually plug in your base station and then, connect your handset through that base station and connect to the 5G core running on AWS, or you can use simulation. So for our demo, we will use simulators. And then this is a fully functional core, so that means you can actually, after you set it up, you can actually connect it to the internet. So so we thought this is a great way for you to get started and learn about what it means to run these type of workloads on AWS. You can also deploy this to support like private network use case, and we've seen other similar project like Facebook Magma, right? Also, the current version already have like 3GPP release 16 support. So let's look at the AWS architecture. So this is the high-level AWS architecture. So what we have done is to fully containerize all the components. So the original community version is just like VM based. So we have containerized all the key components. Also, we have the flexibility to use different types of compute instance. In this particular demo, we're using the Amazon Graviton 2 instance, which will deliver much higher price and performance ratio over comparable x86 instance. And then we'll use a lot of native AWS service. So we'll use Elastic Kubernetes Services, EKS, our managed Kubernetes offering. We will leverage Route 53, which is our managed DNS service, and then DocumentDB, which is our managed database service that is compatible with MongoDB. We'll also use CloudWatch and Container Insights, so you will see some visualization later on. The actual demo will be focused on like 4 parts. One is the building and pushing of the image to container registry, how this solution can be automated and deployed via Amazon EKS. Once it's deployed, how we can visualize some of the key metrics of the deployment via container insights. And then we'll just do a very quick simulation, using simulator. And there's a lot more you can add, yourself, right? You can, as I said, connect it to a real radio network. We've been working with many partners to layer on automation and service orchestration. And of course, there's a lot of things you can explore on using like CI/CD automation on AWS. So this is the more detailed architecture that we'll be deploying. So we'll be kind of coming back to this from time to time. But in a nutshell, this is going to be deployed in, for the demo, it's going to be deployed in the Singapore region. It can be set up as a multi-AC solution, although for demo purpose, we'll be focusing on one availability zone. And will be deployed on a single VPC. So what you will see is that we have multiple subnets. So we have the public-facing subnets, and then we have a number of private subnets, and we partition those private subnets according to like the signaling subnet for control plane, the user plane subnet for all the data plane. And we also, have a subnet sort of specifically allocated for the communication with the document DB. And then in terms of the Kubernetes infrastructure, we're going to have two worker nodes, one for control plane, one for user plane. And you see, we will, through labeling, will ensure that the control plane, containers get deployed on the control plane instance, and then the data plane containers deploy on the user plane instance. And there's other supporting service we will use. So for example, CloudFormation will be leveraged to set up that sort of baseline environment. We will use things like CloudWatch, we'll use container registry, we'll use Route 53, and we'll also leverage Lambda for some of the controller and IP address update function, which we'll talk about. All right, so the first thing we'll do is to build the required images. So what you see is first we'll be pulling from the Git repository, which is part of AWS Stat Samples. And we actually have 4 images that we need for this demo. So one is the Open5GS main software. The other one is the Open5GS web interface. And then we have the, the controller that we'll be using to manipulate our DNS updates. The final one is to help us update our secondary IP address, which we'll explain a little bit more later. So what you can see is we're now building these images. And then you can see there's all 4 of them. And then the next thing we do is we'll be pushing these images to the Elastic Container Registry. So these are the repository we've already pre-created. But before we actually push, we'll make sure that we are tagging these images properly. And then we'll also make sure before we actually push, we are actually logged into the container registry. And then now we can actually push. And you see that the images are being pushed. If we check the repository, yep, the latest image is there. And then the other thing we will do is We'll also upload the cloud formation templates that we'll be using to S3 bucket. So we've pre-created a number of S3 buckets. And we'll use the one open 4G, 5G. And what you see is now we've uploaded those infrastructure templates. And we're now ready to actually start launching the first CloudFormation template which will create the baseline infrastructure. So we'll be using the file we just uploaded to S3. We'll be grabbing the object URL for that. And then we'll populate the stack with a number of inputs. You see there, by default, we're choosing 2 availability zones. Some of the subnet information is already pre-populated. We'll just provide basic things like the document DB username, password. And we're now ready to launch the stack. And then in the interest of time, we'll be fast forwarding to the part where the stack creation is completed. You will see basic things like the document DB is already created, some of the security roles, subnets, also security groups and other things are already pre-created. And of course, one of the most important construct will be the Kubernetes cluster. So here it is already deployed. The VPC is already there. And then as part of the infrastructure template, it also created a Bastion host. So we'd be doing most of our work via that Bastion host. So we're just grabbing the login details and start accessing it. And we'll make sure this Bastion host is set up with like the basic kube control, Helm, and the AWS credentials required, because we'll be doing a lot of work from this Bastion. And then we'll be also updating some of the basic credential configuration to make sure that we are connected to that EKS cluster created by the CloudFormation template. And then before we can actually start further configuration, we need to make sure that we initialize the document DB. So what you see is the document DB, which is an AWS managed services for MongoDB. It's also compatible with MongoDB implementation. We've already pre-created that cluster there. What we do is we just need to initialize it by creating a dummy database or dummy table. And we'll be doing this through the MongoDB shell. So now you see we'll be accessing that shell, and then we'll be just instantiating or creating that dummy database. And then the next thing we do is, as part of the CloudFormation template, There was also we've also created a number of Route 53 DNS hosted zone. And you will see that we'll be leveraging core DNS as part of the Kubernetes cluster. The infrastructure CloudFormation template already created those hosted zone, which actually resolve to the key FreeGPP interface endpoints. So we'll make sure we update the core DNS configuration to point to Route 53. This is to make sure that when we implement, or as you can see now, we've been updating core DNS with the configuration matching what's created on Route 53. So now we're ready to start actually creating the worker nodes. So there's another CloudFormation template which we uploaded to S3, and that is specifically to help us deploy the worker nodes. So again, we'll be grabbing that object URL, and then we'll be launching this CloudFormation stack. We just need to match some of the basic parameters to what we've already created as part of the infrastructure template. And then what you see is, we actually can select what type of worker node we'll use. So we just keep that as the default C5X large for this demo. And then, we're not going to change this configuration as well. So the next step for us is to deploy the worker nodes. Before we do that, I just want to spend a minute talk about how we address the need for multi-home interface for network functions. This is something we need to do because for these 4G and 5G network functions we're using, they're very different from general IT workloads. So most general IT workloads works fine having a single IP address and a single interface. But when it comes to telecom network functions, such as the 4G and 5G core, it's very common to see one application needing multiple interface. You might need multiple interface for control plane or for OAM management interface attachment or even data plane, right? So the way we'll do this is to leverage the Multus CNI plugin in EKS. So Multus is a very well-known, multi-home interface implementation in the Kubernetes community. And what you see, what I've highlighted there is we have two worker nodes, one for control plane, one for data plane. In our demo, we'll be deploying these and we'll attach multiple elastic network interface to these worker nodes so that each one of them will have access to multiple subnets. And then if we go back to the previous diagram, the one from Open5GS, you see the logical representation of these network functions like the green and the red boxes. What you see is quite a few of them actually have multiple interface attached, right? So that means in order for us to support these type of networking construct, we need to make sure that our worker nodes will be able to attach to multiple subnets and interface. And then when we deploy pods onto these worker nodes, they will have access to those multiple interface and multiple subnets. So in order to leverage Multus, we have our teams have implemented a bit of automation. This is more of an experimental implementation. But what this does is we'll be using the artifacts from this Git repository, which comes with a CloudFormation template for building these Multus compatible worker nodes. And then it also comes with a Lambda function, which can automate the binding of address to the Elastic Network interface. So what it means is these worker node will have the first interface that is still going to be managed by VPC CNI. And then the second, the third, the fourth interface will be managed by Multis. And when we spin up a new port, those port will be assigned with those address, including the secondary address. And the association between those address and the ENI will be automated by the Lambda function. So we'll be making sure that we will grab, the Lambda function, and we'll reference that as part of our worker node stack creation. So you see now we're completing the input parameters for the worker node CloudFormation stack, and then we'll be launching it, and then we'll fast forward to when it's already completed. So you see these two additional worker nodes are being created, one for control plane and one for data plane. And they're actually being tagged accordingly. So you can tell by looking at the tags. So they're being mapped to different node groups. So when we deploy our ports, we'll be able to use the node group labeling to make sure that the control plane ports land on the control plane worker node, and then the user plane port land on the user plane worker nodes. So you see now, if we go back to the EKS cluster, these worker nodes are already added. So now we're ready to just do some of the final configuration before we deploy the actual pods. So what we do is just update some of these Docker files to make sure that they point to the Elastic Container Registry, the one where we push our images to. And then we'll also make sure that we update the ones that are responsible for the Open5JS components. So remember, we have 4 sets of images. So we need to make sure that all those image URL are updated. And then we'll also make sure that some of the basic parameters, like the one we just did for MME, are configured. And obviously, we'll update the MongoDB URL. So these input parameters will be passed to the pods when we deploy them and we start them up. We're actually ready to deploy these containers via Helm. So you see it's now deployed. All the namespaces are created. And then plots are deployed into the Open5JS namespace. So we have the full suite of MME, HSS, PCRF, S-Gateway, UPF, and the web user interface. And then these are the services that were deployed. And then the first thing we do is make sure we can access the web UI. So we'll expose the web UI via a load balancer, so then we can access that externally. So we'll check that the exposure command actually instantiate a classic load balancer. And then we're now ready to access that the Open5GS web interface. So now you see we are logging into that interface. So that looks good. We'll be just doing a very basic configuration, basically just provision like one dummy subscriber, which we'll be using later on. And then as you can see, we'll be adding subscribers. So we'll be just providing some dummy data on the IMSI value. So this will kind of uniquely identify that SIM card. I mean, given that this is just a lab test, so we'll leave the rest of this information to its default configuration. We will actually need to capture some of these later on because we need to configure our UE simulator as well. So as you can see, now all these ports are running, so that's a very good sign. And we just do a quick check on the logs. So you see from the HSS log, it's indicated that it's already connected to the MME at a 3GPP level. Same from an MME perspective, it's connected to the HSS. And then if we look at the other ports, we're also seeing some good sign. So another thing we'll look at is the container insights. So this is a native AWS feature which allows us to see all the container statistics and metrics. So once you set this up at a worker node level, then any pods we deploy to these worker nodes, we can start to report metrics. So you see this view here is a very nice sort of map view of the containers that are deployed into the Open5GS namespace. And you see all the free GPP names and all the pods that we've deployed. So this gives us a very quick central way of managing all those pods, the health and the metrics. And if we kick in and change from the map view into the performance monitoring view, what you will see is also very detailed CPU, memory, network, metrics. And we can certainly mostly drill down further, right? Okay, so the last thing we deploy is the simulator for ENOB and the UE. So for this demo, we'll be using the solution from SRS LTE or SRS RAN. So this is another great community effort, essentially open source software for simulating 4G and 5G radio access network and user equipment. So we'll be deploying the software from SRS LTE into the same container namespace Open5GS as containers. So as you can see, this is now deployed. And then what we'll do is to log into that port because we have a few things we need to configure for the ENOB and for the UE as well. So the first thing we'll configure is the ENOB. And then here we will be focusing on like some of the like MCC, MNC parameters also making sure that we match the MME's configuration, plus a bit on the radio side, tracking area code. I mean, all these are basic mobile network configuration. And for the UE, we will make sure we match the configuration we created earlier for the dummy subscriber. So here we'll make sure that we capture that dummy subscriber information and match it with this USIM configuration. So things like IMSI, IMEI, and the SIM security parameters. Okay, so now we're ready to launch a simulated E2B. So as you can see, it's now being started. And then to make sure that it is started successfully, we'll check the logs on the MME. So what you can see there is it looks like with all the parameters configured properly, the E2B is connected to the MME. And then we'll also start the UE. So again, what you can see is there's no notable error when we started the simulated UE. And then you can see that it's showing some of the radio layer is connected and network attached successful, which is exactly what we want to see. And then we will check the E2B logs so you can see the radio parameters coming through. We'll check other logs like on the MME side. Looks good. We'll also check other components like the S gateway user plane. Again, we see the the bearer associated. And then the last one we check is the UPF. So again, that looks good. And then the final thing we do is we will log into using another terminal. We'll just do a very simple connectivity check on the UE. So now you see that this is on the simulated UE. And then we'll do that connectivity check, basically just make sure we have reachability to the gateway address, which sits on the core network side. Yep, so that looks good. So one thing worth highlighting is the great thing about SRS LTE is it can actually allow us to simulate the environment without using a real radio network interface. So in our case, because we're not using a radio access network interface, the real radio frequency. So one thing that is good about SRS LTE or SRS RAN is because we're not using a real RF interface, it actually allows you to simulate the interface between the UE and the E2B using zero MQ. So if you want to read up more on that, then yeah, there's certainly some very interesting thing you can do there. But basically, that's how we can simulate this radio interface between the two between the two process on the same port. So I hope this has been a very useful demo for you. I mean, again, there's a lot more we can do, but we were hoping just to show you something quite basic, like how you can get started running 5G components on AWS. Given that this is an open source project, there's a lot of community participation out there. Of course, we're not saying this is like a production grade solution, but it would be a great way for you to get your hands dirty and also just explore various deployment possibilities on AWS. There's a lot of future extension we are working on, and you can certainly add to that yourself. You can plug this into a real radio network if you have access to one. You can also look to layer on like service orchestration to control different deployment scenarios. We're doing quite of that internally, and hopefully we'll be able to show some exciting stuff to you soon. And then obviously we can also implement like CI/CD automation using AWS capabilities. So I hope that's been useful, and hopefully you enjoy this demo. Well, a big thank you to all of you who stayed through the session. It's been a fairly long session. I hope you have learned something from it and it's been useful for your hackathon ideas going forward. To wrap up, here is a quick summary of the key takeaways. So we start the session by sharing with you some of the actual use case, out of the possible, how we have helped our customers and partners in developing these 5G and edge computing solutions. We also spent a bit of time talking about 5G evolution on AWS. We also give you a quick demo of running an open source 5G solution on AWS. So certainly hope that's useful, and you can definitely leverage what we demonstrate as part of your development efforts. Then we also talk about this cloud to edge continuum, essentially how customers actually want to have a consistent programming model and operation experience, whether they're in the cloud or the edge. And then we spent a fairly sizable time covering some of the foundational AWS service enablers for the edge. So that is by no means the full explanation of those services. And we're more than happy to provide you with learning resource, which we will in the next slide, to help you with continuously navigating and learning about how to use and apply those services. And then the last session, we talk about edge use case realization, really, where we share with you the complexity navigating the edge ecosystem, but more importantly, how you can establish a repeatable, systematic approach by working backwards from your customer in order to get better in developing these 5G and edge computing use case and developing the ones that are more repeatable and more practical. So here's a collection of learning resources. These are essentially a combination of landing pages, white paper, blogs. Some of these links also link to GitHub repository where you can get your hands dirty and start experimenting. So we definitely suggest you to spend plenty of time going through this material. There's a lot of interesting ideas you can extract from there. Play around with some of those demo solutions for sure. And most importantly, have fun, right? Because this is a very exciting technology space, and we're more than happy to, have conversations with you and support you offline along the way as well. So, once again, a big thank you to all of you who have spent the time, to go through this session. Feel free to reach out to me personally either via email or my LinkedIn. I'm happy to, connect and answer any questions or just brainstorm some shared ideas, right? But most importantly, good luck to your hackathon.